The next reaction that we'll look at are reactions with primary amines. So the same process goes into solving this as goes into solving nearly all the reactions, and that is we first figure out who has electrons. Amines typically have a free lone pair of electrons that can react, and who wants electrons, or where is the delta plus in our other molecule, and of course it's at the carbonyl carbon. So who has electrons, who wants them? So the ethylamine will add to our carbonyl carbon, pushing the electron pair out onto oxygen. And you can see in the intermediate that we have a negative charge on our oxygen, or an alkoxide, and we have a positive charge on our protonated nitrogen. So the oxygen will grab one of the protons, pushing that electron pair onto nitrogen to get rid of the positive charge on nitrogen. At this point, we end up with a carbonyl amine, a molecule with an alcohol and amine on the same carbon. Now, if we treat that with a mild acid, we can protonate the alcohol. And remember, hydroxides are not good leaving groups, but water is certainly a good leaving group. It's very stable. So this becomes a good leaving group, so the water can leave, leaving a carbocation behind. Now there's another resonance structure of this that you can draw, where the positive charge, instead of being on the carbon, is on nitrogen. Notice the double-headed arrow now, because this one's going to be a resonance structure of that molecule. Now there's a positive charge on nitrogen. And then if we want to neutralize that, we have something like water react to deprotonate. And that eliminates the positive charge on nitrogen. And we end up with our product, which is called an imine. It's a carbon-nitrogen double bond. So a couple of things to point out about this reaction. One, it's important that there's a weak acid here, because if there was a strong acid, the strong acid would protonate the amine in the first place, and the reaction would never occur because the amine wouldn't have a free pair of electrons. So this needs to be a weak acid. And another important piece of this is that at this point, when we get protonated, you could also protonate the amine. If we protonate the amine, we make the amine the good leaving group, and all we do is go back towards the start and react again. So that doesn't get you anywhere. So that's why, at this point, why we protonate the hydroxide, or the alcohol group. So let's look and see what happens when we do nearly the same reaction, but we do it with a secondary amine. Okay, we'll start with asking the same question: who has electrons, who wants them? The aminonitrogen has a lone pair of electrons. The carbonyl carbon wants them. This pair of electrons goes out onto the carbonyl oxygen to make our first intermediate. In our intermediate, we have O- and NH+, again, just like we did in the last one. So we can get rid of both charges easily by the alkoxide coming and taking the proton off of the nitrogen, giving us a neutral intermediate, which is the carbonyl amine. We can still protonate that with a weak acid. And that alcohol, once protonated, now is an OH2+ group, which when it leaves is water, which makes a very good leaving group. So up to this point, we really have the exact same mechanism as we had with the primary amine, but now we have a problem. The problem is there are no hydrogens on that nitrogen to remove. So in the primary amines, we remove the proton off of the nitrogen to get rid of our positive charge. We can't do that now. So now what we'll have to do is we're going to have to take a proton off of one of our carbons nearby to get rid of the positive charge. And we can just use water again. Water comes by, electrons from the oxygen come by, grab that proton. Now this electron pair goes over and forms a new double bond to get rid of the positive charge. And now we're at the end. Now we don't have an imine anymore. Remember, the imine was a carbon to nitrogen double bond. Now we have an enamine. So it's similar in a way to the enols that we've seen before, where we have an alkene, and then out of one of the sp2 carbons, we have an alcohol. In this case, with our enamine, we have an alkene, and out of one of our sp2 carbons, we have an amine group. So secondary amines, when they react with a carbonyl, form enamines, while primary amines, when they react with the carbonyl, form imines. You don't have to memorize that. If you just follow through the mechanism, eventually, hopefully, it makes sense. And the difference really is that here we don't have an NH, so we have to grab a proton from one of the carbons nearby. The next reaction we'll look at is we can do a hydration reaction of aldehydes or ketones. And we can either do base catalyzed hydration or we can do acid catalyzed hydration. So I'll start with base catalyzed because it's actually a little bit easier mechanism to draw. And at any point in any of these videos where you want to stop and pause it and try to see if you can draw the mechanism first before you watch the video, I think that's a great idea. Because in the end, almost all of these reactions use at least part of the idea is the same, and that is who has electrons and who wants them. Some of the mechanisms, like the enamine and the imine ones, get a little bit longer, a little bit complex, but at least the first few steps of a lot of the mechanisms you should be able to determine. So hydroxide has electrons, carbonyl carbon wants them. Electron pair from the pi bond breaks and goes out onto the carbonyl oxygen. We have our alcohol and our alkoxide on the same carbon. Really the only thing left to do is to protonate, and we get a geminal diol. Gem or Gemini is from the symbol for twins, and so since these two alcohols are on the same carbon, it's like they're twins, and so that's why it's a gem diol. Now you can do nearly the exact same thing with acid and water. There's just a little bit, there are just a couple more steps that you have to do. If we do acid and water, first thing that happens, who has electrons, is the carbonyl oxygen. Who wants them is the proton. So we protonate first. Once we've protonated, now our carbonyl carbon is reactive to the weaker nucleophile water, which is a much weaker nucleophile than hydroxide is. The water will add to the carbonyl carbon, pushing the pi bond out onto oxygen to neutralize the charge. And now we need another water molecule to come along to remove one of the protons from our OH2+ to make our gem diol.